Welcome to another video for Stat 212. In this video, we're going to be looking at probability models. So a probability model is just kind of a way to organize an event, or maybe not an event, but kind of like a set of possible outcomes and looking at the probability of each of those possible outcomes. So this kind of helps us think a little bit more about long-term probability and long-term likelihood. Whereas in chapter 4, we focused a little bit more on the likelihood of just kind of one particular event, a one-time thing. Now we're going to begin to think a little bit more long-term and get to this idea of variables that have a distribution that tell us what should happen over time. So random variable is a term that we'll start to use here. We won't use it a whole lot in the class, and we're going to use a pretty informal definition, and that's just a variable where all possible outcomes can be assigned to numeric values, and each outcome or outcome range has a particular likelihood of taking place. So as an example, if I think about a one-sided die, a six-sided die, there's 6 possible outcomes. So the random variable there would be the 6 different outcomes that could happen, 1 through 6. And we could also note the likelihood of each of those different possibilities for that random variable. In this case, if it's a 6-sided dice and it's a normal equally weighted die or whatever it is, then it's going to be 1 out of 6 or 0.167 as the probability for each of those possible outcomes. So that would be the probability model for rolling a 6-sided dice. And over time, we would expect to see each outcome about the same amount of times. We could also think about a random variable when our responses are categorical, but we would just need to convert that to a numeric scale first if we're going to call it a random variable. So random variables require the outcomes to have numeric labels. So if we're talking about flipping a coin, we could assign heads to 0 or tails to 1 or vice versa. It doesn't really matter, honestly. And then note the likelihood of each of those 2 outcomes happening. So to kind of get into the headspace for this, let's look at a trial or situation where maybe you don't already know what the probability model is going to look like, but we can go ahead and kind of calculate what should happen. And that is rolling 2 dice and adding the sum of those results up. So if you think about D as a random variable, and it's a random variable generated from rolling 2 fair 6-sided dice and recording the sum. So the first question we have is, what is the sample space of D? What are the different values that D could take? And then secondly, are all these outcomes equally likely, or are some more likely than others? And can we kind of record the probability of each of these outcomes for D in the table on the right? Now, I'd encourage you to take a few minutes and pause the video on your own and think about these 2 questions and see what headway you can make on your own. I will obviously continue on the video and talk about this. But if we think about the range that D can take, the smallest that D could be is 2. And that's because the smallest sum that I could get is going to be produced by rolling a 1 and a 1. So if I have 2 1s, that would give me a sum of 2. And there's only one way to do that. So there's only one outcome that gives me D equals 2. I could also get D equals 3 if I have, say, a 2 and a 1. And this might be a little bit strange, but I could also get a 1 and a 2 in the other order. And you might think, well, that shouldn't count. That's the same result, isn't it? But it's actually not if I'm thinking about the fact that I have 2 different dice. And I could have, let's say I have a blue dice and a red dice. I guess I should be calling them die, honestly, if they're singular. If I have a blue die and a red die, well, I could get a blue 1 and a red 2, or I could get a blue 2 and a red 1. And those are 2 different outcomes. Those are 2 different things that could happen that both give me a sum of 3 and both give me, a 1 and a 2, but on the other dice. So if you think about it like another way, it's kind of like if you think about a family and like if you think about, having children, and you could have, the oldest be a boy and the youngest be a girl, but you could also have the oldest be a girl and the youngest be a boy. Well, those aren't the same things. Like those aren't the same outcomes. Even though they both have like on paper kind of the same result, those are 2 different possibilities, or there are 2 different orders and outcomes. Okay, so we could have d equals 4. We can kind of continue on and think about the different possibilities. I could have, let's see, 2 and 2. I could also have 1 and 3. And then again, I can have 3 and 1 in the other order. Now, I can't really have 2 and 2 in different orders because that is the same thing, right? I can't, like, if I have a blue 2 and a red 2, well, that's a blue 2 and a red 2, and there's no switching that order. But the 1 and the 3, I can switch around. So we could continue on and label all these different outcomes. And if we get all the way to 12, that would be our maximum, and we're going to be back down to just one possible outcome here, which I think is kind of interesting, right? So an 11 is going to be two different outcomes, so it's going to be like a 5 and a 6, as well as a 6 and a 5. And this trend is going to kind of look like this, where it peaks around 7, or it peaks at 7, I guess, and then gets smaller and smaller at kind of the fringe outcomes here. So there's a lot more ways to roll a 7, a 6, and 8 than there are to roll like a 2 or a 12. So then our sample space we can write as all the values from 2 to 12. And then the probability for each of those, we could kind of calculate. So there's 36 different possible outcomes. I can think of that if I multiply 6 by 6. So there's 6 possibilities for dice 1, 6 possibilities for dice 2. So that means there's 6 times 6 possible outcomes total. And there's 1 out of 36 ways to get a 2, 2 out of 36 ways to get a 3, and so on. And then we're going to find that it would peak at 7. That would be the most combinations, as there's 6 combinations that add up to 7. And then they're going to fall back down here. I'm not going to turn these into decimals, but I will go ahead and do the first one. The first one would be about 0.0278 if I round it, but I won't bother with the others. It's not necessarily important. So what we did here is we use our knowledge of probability and this process and calculated the theoretical probabilities of each of these possible outcomes for random variable d. And we happen to know that information. It's not super tedious to do. It's a little bit tedious, but it's something we could certainly do. However, I also want to mention that a lot of times we're working with probability models that are kind of unknown to us, perhaps because there's a lot of outcomes involved, or it's just really difficult to probabilistically calculate the likelihood of every outcome. We can also use simulation-based modeling in those cases. So this is really common for statisticians to do, especially kind of in the modern era of statistics that we've been in since computing became widely available, is that we could just use a program like R to simulate, basically set up a situation and then simulate the trial, thousands, tens of thousands, maybe even hundreds of thousands of times, and then just observe the probability model that emerges. And we can use that to kind of approximate what that probability model really is, because there's this thing called the law of large numbers that if you have a lot of trials of something, then the true probabilities will kind of emerge from your results. So what I did here, there's some code that simulates this process of adding up two six-sided dice 100,000 times and then recording the results. And I'm actually going to do that over here in R. I'm only going to do it 20,000 times for two reasons, though. One is that when I'm using this program to record my videos, it takes up a lot of CPU, and R goes a lot slower for that reason. The other reason is because I'll still get reasonable results anyway, so it's not crucial that I do 100,000. I just need to do enough that I can kind of see the results emerge. Now, we haven't done loops in this class, so it's okay that some of this code is not going to look familiar at all, and that's okay. You don't necessarily need to know it. Maybe some of it you can kind of figure out what's going on, but long story short, what we're doing here is we're setting our trial number to 20,000. We are going to kind of create two dice that go from 1 to 6. So if I kind of enter these here, sorry, my cursor is enormous on this screen, the way that I'm doing this. I'm going to actually go ahead and run all of this here. So I have like 2 sequences from 1 to 6. I had this thing called result that is null right now that I'm going to fill with results from my trial, and I'm going to simulate this, in this case, 20,000 times of adding these results up and just kind of adding them to this vector called result. So I'm going to do that here. It will take maybe like 20 or so seconds to run, and I'll also kind of move myself out of the way. Or actually, I think it's already done. That's good. So I'll move myself out of the way so we can see what happens. And then I'm going to look at this table result. So I'm going to take all my results, divide them by 20, and I can see how often probabilistically I'm getting a sum of 2, 3, 4, 5, etc. So I can see it peaking around 7 and kind of tapering off around 2 and 12. These probabilities, again, are not exact, right? So 2 and 12 should be the same. They should be about 0.0278, but they're not exactly that because I only did 20,000 trials. But if I did more trials, these results would converge more closely and more reliably to those true underlying probabilities. So this is a great strategy to use when you're working with distributions that you don't know. It's more just kind of for demonstration and FYI in our class, not really something we're going to do. However, there is kind of a challenge question down here that is going to be part of your extra credit in this unit. So there's kind of a task down here, digging deeper, where you have a 6-sided dice, an 8-sided die, and an 11-sided die, and you can use that same setup with a little bit of adaptation to figure out how often you should get different results, summing those up. And in this case, you're trying to compare the sums that are odd versus the sums that are even, and see if they're equally likely, if it's a fair game, or if they're unequally likely, if you're more likely to win or lose. So there's a little bit of kind of helper code down here that you'll have to run as well. But again, you can just kind of use that same template with a little bit of adaptation there for this context. We can also briefly talk about the expected value of a discrete random variable. So discrete meaning that we have kind of these whole number possibilities like 0, 1, 2, 3 for our random variable. So an expected value is essentially like a mean, except that it's more a probabilistic calculation. It's saying it's the value that would kind of average out over time. And so we call it an expected value because if I'm kind of simulating from a probabilistic process, it's kind of my best guess, it's my most centered guess for what should happen. So we can calculate an expected value from a probability model by summing up all of our random variable outcomes times the respective probabilities. So for example, with the dice, we could do 1 times 1 over 6, plus 2 times 1 over 6, plus 3 times 1 over 6, etc., to calculate the expected value of rolling a 6-sided dice, and it should come out to 3.5 if you did that. And here we have an example. What is the expected value for the dice game that we modeled previously? In other words, where we're summing up 2 6-sided dice. So that's going to be 2 times 1 over 36 plus 3 times 2 over 36 plus 4 times 3 over 36, right? And so we can keep going, and then we're going to end with, we'll have 11 times 2 over 36 plus 12 times 1 over 36, right? So each outcome of our random variable, each possibility of our random variable, times its probability of taking place. And by doing that, we kind of get like an average result. We get kind of an average outcome from our probability model that we're going to call our expected value. I won't calculate it because that's a lot of tedious math for you to watch, which doesn't really do anything, I don't think. However, we can do another example here that's a little bit simpler. So here we have a traditional roulette wheel. It has 37 spaces, 18 are red, 18 are black, and 1 is green. Let's say that I've bet in such a way that if the ball lands in the red, I win $1. If it lands in black, I lose $2. And if the ball lands in green, I win $10. Let x be the random variable representing my winnings. So the first thing we're going to do is set up our probability model on the right. So we have this kind of random variable that takes 3 different values, right? So if I'm playing a game, the random variable I'm interested in is my winnings or losses possibly. So I could win $1, so I could have +1. I could lose $2, which is going to be -2, or I could win $10. So it's going to be 1, -2, and 10. Now, the probability of each of these outcomes depends on what the color is that we're working with, right? So for winning $1, that's going to be landing in a red, and there's 18 out of 37 ways to do that. Losing $2 is also going to be 18 out of 37 possibilities, and winning $10 is going to be 1 out of 37 possibilities. So there's our probability model on the right. We have our outcomes represented as our winnings. We have our probability represented as the likelihood of landing in each of those assigned spaces. Second, we can calculate the expected value of our winnings. So we can multiply +1 times 18 over 37. We can multiply or add -2 times 18 over 37. And then we can have 10 times 1 over 37. So I'm going to calculate this out. So it's going to be 18 over 37 minus 36 over 37. So 18 times 2 is 36. So minus 36 over 37 plus 10 over 37. And I get negative 0.216 approximately. So how can we use this result to answer this next question? If I continue playing this game, should I expect to win money or lose money over time? So think about this on your own for a second. We calculated the expected value. Does this help us answer this question, and how so? So I would say the answer is that we should expect to lose money over time, most likely. The longer we play, the more likely we are to be losing money. And the reason is because our expected value is below 0. It's a negative number, meaning that the more games we play, the more our probabilities on average should converge to this expected value. So if I keep kind of adding up my winnings, right? So my probabilities of winning $1, probabilities of losing $2, and probability of winning $10 over time should converge to these particular probabilities undergirding the process. Now, if I only play a few games, I might see these $1 a little bit more often or a little bit less often, but the longer I play, the more these probabilities are going to converge to these values, meaning that I should be expecting to lose about 21 cents or 22 cents per round that I play. Again, it's just an estimate. I could play 10 rounds and be ahead, right, depending on my results. But the expected value is telling me over time what should happen is I should be losing about 21 cents per round that I play on average. All right, and then kind of one note down here as well. So the examples that we've used in this chapter, you might have noticed that we've used a lot of game examples, and that's really common when doing probability because when we're working with games, we usually have known probabilities of the process. And so that means that we can calculate theoretical probability models, meaning that this is how the process should go. So it's kind of a helpful way to start working with probability. However, in real life situations, we're often going to be working with empirical models, and there's 2 common ways that we're going to see that. One is an experimental probability model, which you might also associate with the term frequentist if you take more statistics classes. An experimental probability model is calculating probabilities based on collected data. We use our collected frequencies for each category or outcome to build a preliminary model, like how many observations out of the total had this outcome. So for example, that simulation-based modeling that we saw earlier was an experimental model. I mean, in that case, we're just simulating it a bunch of times. So it's kind of like, taking advantage of simulation. But that general strategy of collecting data and then just calculating what are our probabilities so far is kind of like approximating a model. And hopefully we have a lot of data such that we can make reasonable predictions with our experimental probability models. But I also like to mention, especially if you're in biostatistics, that you might encounter Bayesian probability models as well, which are going to be a little bit more subjective. These are going to use a combination of collected data and a prior model to develop a balanced final model. So a good example I like to use, if you know what 538 is, it's like they do a lot of sports and political modeling. And so they would be using Bayesian models because they don't base their predictions purely on collected data. They're also using these priors about demographics and past elections or different things like that. So if you think about like polls can provide more of this like frequentist type data. But if I combine polls with other information like, well, these polls were based in, say, September, and the election's coming up in November, and it's more likely that like we expect the economy might take a downturn, or we expect this to happen or that to happen. Well, then I'm kind of building in prior information and adding it to my experimental model with the polling to create kind of this combined Bayesian model. So you'll see Bayesian models a lot in biostatistics where you combine data along with prior understanding of what is probably going to happen as well to come up with some kind of balanced model. So this is where probability and statistics really meet, is when we get to these experimental or subjective modeling, is because instead of just knowing fully the truth, rather we're starting with some collected data and trying to make statements about what could be the truth, right? So that would be the process of inference. So these kinds of ways of thinking are going to really be what statistics is about, whereas this theoretical modeling is more the study of probability. It's more of a mathematical discipline that just kind of provides a basis for us when we get to thinking about how we do inference.